Please, thanks.
All right, thank you, Leah. All right, so yeah, I guess this is a little bit of a more informal conference series. So I tried to make my talk a little bit, well, a little bit less formal. So yeah, I have a little bit of a recurring theme going on, getting in this talk a little bit. You can find it, and it seems like the carbon-12 alpha gamma reaction is a fitting reaction to study at Notre Dame, such a holy university. It's known as the holy grail of nuclear astrophysics. And I'll talk to you today a bit about why it's so important and try to give you an understanding of the reasons that people have looked for this, tried to study this reaction for 40 years or so, because it's not necessarily obvious. So I'll give you a bit of an astrophysics motivation for this, and I'll talk about a bit about the history of this reaction, because it's a history of not just the study of this reaction, but actually a lot about how reactions evolved in nuclear, at least in nuclear astrophysics. And then I'll talk a little bit about some exciting new measurements that have been done recently that have really improved our understanding of this reaction. And then I'll talk about sort of the part that I've worked on most, which is what happens when you try to take all the data and analyze it simultaneously. And then I'll give some conclusions about where we need to go in order to sort of reach our goals with the understanding. That's correct. Okay, so carbon-12 alpha gamma is very wide-reaching as far as how it affects nucleosynthesis and the evolution of stars in the universe. And I'll just start with the hydrogen burning. I'm sure most of you know that for heavy mass stars, hydrogen burning proceeds through the CNO cycles. And the seed nuclei there are carbon, nitrogen, and oxygen. Of course, the ratio of the seed nuclei, carbon and oxygen, that are present in that star, determined by carbon-12 alpha gamma reaction in previous generations of stars. So it has even a significant impact in the earliest stages of the star's life. Of course, helium burning is the main place where carbon-12 alpha gamma takes place in the star. Core helium burning, shell helium burning, and then even in explosive scenarios. And the carbon-12, the first reaction that occurs after hydrogen has been exhausted in the core of the star, is the triple alpha process. And then after a significant amount of carbon has been produced, the carbon-12 alpha gamma reaction is the next one that can proceed. So you may remember that this simultaneous fusion of 3 alpha particles is necessary because there are no stable nuclei in mass 5 and 8 to get up here. So you have to have this triple reaction, which is quite unlikely, and it took a considerable amount of time to understand that this was the way the nucleosynthesis, so that the star actually proceeded to create carbon. I think it was Salpeter who figured this out, and of course Hoyle also figured out that there was actually a resonance in beryllium-8 plus an alpha particle that enhances this cross-section greatly. It's a sharp, narrow resonance, and so the triple alpha reaction rate is determined almost entirely by a single narrow resonance in soil state. And the properties of that resonance are quite well known. So the uncertainty in the triple alpha process is fairly small. Even this, though, it's hard. I spent a lot of time trying to actually find out what the uncertainty was on the triple alpha process. And even in a review article, they don't really say. They just say it's pretty small. So probably something like 10% on that order. But the carbon-12 alpha gamma reaction that happens next also has an enhanced cross-section, but it's not because of a single narrow resonance. And it's actually because of some subthreshold state resonances that we'll get to. And it turns out that because of that, it's much more difficult to measure and therefore determine the cross-section for this reaction. And so that's why this is sort of called the Holy Grail. This is such an important reaction because all stars have to go through this nucleosynthesis chain. There's no other way around it. And so this really has an effect on all later stages of stellar burning. And so a large uncertainty in any one of these reactions, or at least the first two, creates large uncertainties that propagate throughout any kind of stellar model. So this really stops here with O16 alpha gamma, because unlike the first two reactions, O16 alpha gamma doesn't have any resonances at low energy to enhance its cross-section. So it turns out that things like carbon-12 fusion and carbon-12 O16 actually end up having larger cross-sections, and they're able to ignite even before this other reaction becomes efficient. So this is really the end. This very simple, really two-step reaction chain is really all of helium burning. And it's a really nice diagram that I like on the right that Frank Timmy's created for a paper that I've been working on with him recently about. You can see in this paper at the bottom is the helium mass fraction, and the y-axis is the mass fraction of carbon-12 and O16. And what this represents is as the star evolves and it burns the helium in its core, it starts with 100% on the left, and then it moves down to 0, and it shows how the carbon-12 and O16 build up in the core of this particular model that he's used. So for light mass stars, of course, they're not massive enough for their core temperatures to get hot enough to burn carbon and oxygen. And so they end in a white dwarf, say something with an initial mass of less than about 6 solar masses. And it turns out, of course, then the carbon-12 alpha gamma reaction then determines really the ratio of carbon-12 to oxygen, which is what most of this object is made up of. And so it really determines a lot of the characteristics of a white dwarf, and especially if that white dwarf is in a system where it has a companion star, where it can accrete material off of that companion that's still on the main sequence and produce a type 1a supernova, then this amount of carbon and oxygen that's on its surface has a strong effect on the properties of that supernova. I just realized that all this is covered by the window. Yes. Yeah. Okay. Here. Okay. So if a star has greater mass, say something like 8 solar masses or larger, then it can begin to burn heavier elements. Of course, here's the sort of cartoon with a simplified kind of onion model that we all see in elementary school of a heavy mass star. And what's interesting here is that you have a competition between carbon-12 alpha gamma and O16 alpha gamma for these more massive stars. They have a higher core temperature, and they compete with neon-22 alpha N. And during helium burning, remember you have the S process going on, where things like neon-22 alpha N and carbon-13 alpha N are producing neutrons, and they're capturing a heavy seed nuclei that are creating all these heavy elements. And there's actually a close competition between these reactions. And basically, carbon-12 alpha gamma is acting as kind of a poison that's stealing the alphas from neon-22 alpha N. So it actually even has a strong effect on how the S process happens in stars. And of course, we have, as I said, once this star is massive enough, it then has, of course, the strong effect on how carbon-12 fusion goes. So basically, right from this previous slide, we had how the star sort of ends up determines the difference in the reaction rate has an effect on this ratio of O16 to carbon-12 left after helium burning. So it has a strong effect on carbon ignition. So here's this very famous plot where I feel like I have to show this if I talk about carbon-12 again at some point by Weaver and Woosley. That was really, at least in the 90s, became a strong motivation for studying this. So this is a model that shows how depending on, if you change the carbon-12 alpha gamma rate, which is down on the x-axis here, as you change that by different multiples, how it affects then the different fractions of nuclei that are created for a massive star. You can see that it's quite sensitive. There's a large difference. All right. So after working on a recent paper here, I was really interested to learn about the fact that carbon-12 alpha gamma also has an effect on even the first stars, the so-called population 3 stars. And it turns out that if you have a star beginning of the universe, of course, there's no carbon, nitrogen, and oxygen. And a lot of these early stars are very massive. Models predict that they're 10 to 100 solar masses, or huge stars. And so it turns out that they end up creating their own CNO elements in them as they evolve, even in their own lifetime. So they get hot enough that they start to go through activate carbon, or the triple alpha process in carbon-12 alpha gamma, and then they go back and, I guess, concurrently burn through the CNO cycle as well, the hydrogen in their hydrogen cores. So that's rather interesting. Okay, so what's our quest here for this reaction? So the stellar modelers tell us, and this is sort of a blanket statement that everyone uses with this, and it's a little bit of an excuse because this is a tough thing to figure out exactly with many reactions. How well do we really need to know it? But at least our best estimates are that we need to have the reaction rate of carbon-12 alpha gamma known to about a 10% uncertainty before it's smaller than other uncertainties in the stellar models. And as I'll show, we're not quite there yet. Most estimates put us at about 20%. And some people have argued that this is even much larger than that. But there's a recent paper from 2012 that said, actually, maybe we know this even as well as 13%, which is really an unprecedented level of uncertainty. And that was one of the big motivations for me looking into this, was to try to understand, try to kind of cross-check this analysis and see what I could come up with. So the big problem, right, with carbon-12 alpha gamma is that on the right here you have a plot of the cross-section on the top and then the S factor on the bottom. And if you remember, the S factor is just the cross-section would be L equals 0 angular momentum, Coulomb penetrability basically divided out of it to really enhance just the nuclear part of the cross-section. And you can see that the blue line represents the lowest energy measurement that anybody has ever made for this reaction. And that's at about 1/10 of a nanobarn for cross-section. And that's pretty tough to do that measurement. And in fact, the uncertainties there are nearing 100%, really, for those measurements. They're sort of just barely a signal. And in order to measure it at really the energies that we're interested about, at least in normal helium burning, you have to get down to about 300 keV. And at that energy, the cross-section is something like 10 to the minus 17 barns. So it's unlikely that we could ever measure this in a laboratory, at least the kind of laboratory that we can imagine currently. So the whole problem here is that you have to extrapolate the cross-section over several hundred keV. And that turns out to be quite a challenge. Okay, so the most challenging part of this is that there's no nuclear theory that can predict this capture cross-section, at least to the precision that we're trying to get to. So there are nuclear theories that can probably predict this to, maybe 30–40% uncertainty, something like that perhaps. So I'm talking about theories that are based on, not really ab initio yet, but potential model and things. Even these have tunable parameters in them, so they're not, but they're more fundamental, a little bit more fundamental. So the solution, and this has been the solution since the 70s, has been to use some sort of phenomenological model, some kind of, to fit the data. And so what's necessary is to have a very good understanding of the level structure, and that at least we have. O16 is a light nucleus. It doesn't have a very high level density. It's been studied incredibly by every different thing that you can think of in nuclear physics. So we know what the level structure is very well. But you have to have actual data to constrain this sort of phenomenological model. And in the second part of my talk, that's what I'm going to basically focus on, is how do you do that? So if we have to rely on this phenomenological thing, and I'm going to explain also what I mean by phenomenological a bit more. If you're not familiar with what that really means. We have to sort of tailor our measurements to constrain this model if we want to get a better, use it to have a better, get a better extrapolation with it. And how you do that also isn't necessarily obvious. So let's dig into the nuclear physics a bit of this reaction. So as I said, carbon-12 plus an alpha forms O16, and it populates these different levels. And on the right, what I've done is I've plotted different reactions that you can do in the laboratory, that you can measure in the laboratory. And I plotted them, instead of versus beam energy or versus center of mass energy, I switched it to the excitation energy of the compound nucleus. And so you can see there's this lowest energy 1- state, and it corresponds to this lowest energy resonance in carbon-12 alpha gamma. But it also corresponds to resonances in other reactions. The cool one is beta delayed alpha nitrogen-16.
It's broad, right?
Yeah, it's very broad, but it has the same width, of course, as this resonance, because of the same level. And you can see it as well in carbon-12 scattering, alpha scattering, right? And all of these, right, these levels, they have the same characteristics. So you can use other reactions to constrain, add further constraint on the phenomenological description. And what I'm talking about is you really, right, you want to know what the width of this lowest energy resonance is very well. And maybe it's hard to measure it in carbon-12 alpha gamma, but you can measure it by beta delayed alpha emission, and you have a huge number of statistics. It's much easier. Or alpha scattering as well, and you can have a really an enormous constraint on what the total width of that resonance is. And again, this is a capture reaction, so it's much weaker. It's really a perturbative reaction compared to the nuclear reactions like the scattering. So the gamma width turns out to be much smaller. So it really doesn't even actually, in fact, in the theory, it's even neglected in the total width. So you really have just the total width can be determined through these indirect measurements. And then we'll see fewer parameters, or at least that parameter is very tightly constrained. You can also use other kinds of reactions like alpha transfer and even lifetime measurements, which are often done with inelastic electron scattering or gamma-gamma types. And so there's a wide range of reactions that you can pull together information to really try to nail down this cross-section. So I'll talk really briefly about this phenomenological model, which is our matrix, and I don't want to get into it too much, especially in this short time, but I want to just say that you have some sort of model, or imagine a model that you can use to predict the shape of, say, sort of the generic shape of a resonance. And more importantly, you have a model, or say a reaction theory, that can tell you also how if you have two different levels of different spins and how those things interfere with each other, how their wave functions interfere with each other. And that's what this really does for us. But what we don't know is the specific details. We know that there are levels and we can put them into the theory, but we don't know the widths of the levels and we don't even know the energies of the levels. We have to have data that tells us that information. So it turns out that what you do for this theory is you define an internal region that is spherical and it fully encompasses all the basically the nuclear force, right? The nuclear force ends very rapidly, and you just make this thing large enough so that it encompasses all of the nuclear force. It becomes negligible at large distances. And that ends up being, in practice, something that's, say, 5 femtometers or something. And then outside of that, and you can write down even some wave functions for that in a very generic way. You can't write down what they are explicitly. That's the whole problem. But outside, you assume that the only thing happening is Coulomb. And you can write down the solution to these Coulomb wave functions outside, in the outside region. And then you can go through and you can try to solve this and there are, of course, prescriptions for how you can get to the cross-section from this. And it ends up that at some point you have to do this integral that's down here on the left, and you don't know that internal wave function. You don't know how to solve that integral. But that integral is just a number. And that number becomes the fifth parameter. And you can write that, these lambdas reduced with amplitudes is what they're called. They form the R matrix. And you can see that the R matrix is a sum over lambda, which is a sum over different levels in the compound nucleus. So you're explicitly putting in one of these sums for every single level that you have. You have to put that in just yourself into the theory. And then, I've written just on the bottom here how in some way you can get to a T matrix, which is proportional, the square is proportional to the cross-section. Okay, so one of the big confusing things about our matrix and how that relates to sort of the more standard or simplified theory of a BREIT-WIGNER cross-section is that, right, it turns out when you derive this more formal theory, you don't get partial widths like we're used to measuring. You get these reduced width amplitude things, and the problem is they're not directly related to a width. You have to do some kind of a little bit ugly approximations to make sort of force this theory to look like a BREIT-WIGNER function. First, you could do a single level approximation, and then you have to do, it turns out, some kind of series expansion in the denominator. And once you do that, you also have some boundary conditions I talk about that you have to set to some magical values. And when you do a bunch of tricks, you can finally make something, force this theory into something that looks like a BREIT-WIGNER. And then you can use widths and things that you measure, that we measure through other kind of reactions to try to constrain this theory. Okay. So this all is explained in the seminal work by Lane and Thomas, which is in Reviews of Modern Physics. It's pretty nasty. It's tough to read. But it has everything in there. It's a really impressive article, actually. But it's definitely not, you have to read it about 7 times to figure anything out in it. But as I said, yeah, you're inserting these levels independently, and it's very completely data-driven to constrain it. And on the right, you can see sort of like a cross-section calculation from one of these models. The black line is the total cross-section, for example, for the E1 transitions in carbon-12 alpha gamma. And the red lines show just if you had just one of those resonances by itself. Just do a calculation, you say, okay, there's just one of these. But you can see, like in the top of this middle region, the individual things are actually larger than the sum, right? That's because the interferences don't add necessarily. They actually can add and subtract in between resonances. And so you get these interference dips that can be smaller than the individual contributions. And that's extremely important for this kind of modeling this kind of thing. And that's why in the earlier measurements or earlier analyses that just looked at used BREIT-WIGNER functions, it was pretty tough to do this. They introduced some like ad hoc interference terms, but they didn't have the full theory because it's pretty tough to work out, actually. But once you get it, then you can do this kind of thing. The other problem is there are background terms. So as I said, we added in all these resonances individually, but there are an infinite number of resonances that extend to infinite energies. And all of these resonances have tails that expand down to zero energy. And so they might have some effect even on a low energy cross-section. And the only way that you can constrain this is by having data to do it. So there's a lot of ambiguities in this kind of analysis. So let's see. We've gotten very far. All right, so I'm going to just kind of go through a quick history of this because I think it tells us something about how tough it is to do this. And the first measurement or attempted measurement that I could find of carbon-12 alpha gamma was by these guys, Allen and Sarma. They were in the UK at that time, and they tried to measure at about 1.6 MeV, which it turns out was a pretty crazy thing to do because the cross-section there is about 2 × 10⁻⁻10 barns. And they didn't see anything, so that was correct. There was definitely, they were not going to see anything there. Later, people tried at a bit higher energy, and they were able to see some kind of signal. Turned out that's 3 to 3.45 is on the top of this lowest energy resonance. And as time went on, people sort of were able to start studying this low energies, and originally not for nuclear astrophysics, but isospin mixing in carbon-12, which is rather interesting in its own right, but structure detail. But this is an extremely hard measurement, as it turns out. You'd think that helium on carbon would be easy. Carbon is extremely abundant. You can make a nice carbon foil. You know, what's so hard about that? But the problem is natural carbon isn't just carbon-12, it's also carbon-13. It's only about, I think, 1% of carbon-13. But if you look, it's not hard to see up on the left here, you can note that this is the carbon-13 alpha N cross-section compared to carbon-12 alpha N. That's too much technology. Oh, that's true. Fine. All right. That is okay. So yeah, in this plot you can see that here's carbon-13 alpha N, carbon-12 alpha N at the bottom, and you can see that it's like 8 orders of magnitude higher in cross section. So even though a natural abundance is 2 orders of magnitude less, and even though you can even try to make an enriched target, you still have carbon everywhere. It's in your beamline, it's on your slits, it collects all over the place, and you're going to hit some carbon-13. And what happens is it produces a large amount of neutrons, which kill germanium detectors very quickly, and causes and even produce secondary gammas through NN prime reactions and N gamma reactions that contaminate your gamma ray spectrum. And it turns out to just be a horrible mess. And that was really what still does impede most measurements with this. Here's one of my favorite measurements. This is really a measurement that was done at Caltech in the 60s, and they measured all the way from, say, 3 to 8 MeV. This is the widest energy range I think that anybody's ever measured with carbon-12 alpha gamma. The guys at Caltech in the 60s really knew what they were doing. I mean, this experiment is pretty interesting because it has a whole list of people on here that are thanked in in Larson's thesis: Lily Fowler, Charlie Barnes, Fred Barker, who's our matrix expert, Ralph Kavanaugh, Tom Tombrella, who are all really great experimentalists of the time. So here's the first accurate measurement that was made by Peggy Dyer and Charlie Barnes at Caltech. And this measurement, I think, is amazing. This was done in 1974, and the black points are their measurements from that time. And here's a measurement that was done in 2012. That's shown in the shown by these starred points over here. They didn't really do any better, almost. And this is tough, because I plotted this on F factor, but really this cross-section drops. You know, it's down, right now it's down in that 10th of nanobarn range. It just gets incredibly difficult to get better here, just brute force directly. I think I'm rapidly running out of time. And at that time, when they did this, it was actually, they thought it was only E1 transitions that dominated the cross-section at low energy, but it turns out that there's actually a strong E2 component, which makes the modeling very difficult. There are a lot of nuclear models that can model just E1, and a lot of them can model just E2, but mixing those things together, it turns out, ends up being very difficult. And it was Karl Kettner in Germany who figured that out in the 80s. It really took 10 years, and Klaus Rolfs figured that out. It also turns out, this, as I've alluded to, the cross-section is determined primarily at low energy by sub-threshold states. So if you look at the level diagram over here, there's these 2 sub-threshold states at 7.1 and 6.9 MeV. They're right below threshold, and they're low energy or high energy tails actually are the dominant thing in the cross section, which you can see up here. Right? This red line is actually this contribution from these sub-thresholds, and it's even more pronounced than the E2. It's really all the E2 at low energy. This also took a long time to figure out back in the old days. So people quickly figured out that this was tough to measure, and even in the 60s, they did alpha transfer reaction measurements to try to indirectly determine the properties of these sub-threshold states. And they also did all kinds of, things like inelastic electron scattering and gamma-gamma, using Bremsstrahlin beams, to determine the gamma widths of these sub-threshold states, which is what you need to model the cross-section. And also in the 60s, they even did these beta-delayed alpha measurements. And so really all this stuff was quickly sort of understood what sort of the different things were that you could do to try to figure this out. And as well as some nice elastic scattering measurements that were done as well here. And in 1970, Fred Barker, who was a famous R matrix theory person who was at ANU, Australian National University, for many years, did a very comprehensive analysis using all of this different data and putting it together. And he ended up with a central value, or low energy, of about 150 keV barn, but he had a huge uncertainty on there, probably because of the data. Well, you can see that he at that time even used some very preliminary data to try to do this. But even then, at the sort of the earliest times, they knew basically everything that they had to do to figure this out. It was just a limit in both experimental experience and a bit in the theory experience to get this. And really, we spent the last 40 years refining these same measurements. So I'm going to skip a lot. There are, of course, many, many measurements that have been done since then. And I'll just quickly skip through some of these. All right, so why is there such a large uncertainty quickly? Most of the measurements, there are about 13 now that have been done at low energy. You can see them by these weird different colors down here. Cover just sort of this kind of narrow, this single energy range. But it turns out that the largest uncertainty that's created is by the properties of these subthreshold states, which are kind of hard to get to these transfer reactions, and by the background, how much the tails of these higher energy states contribute to the cross-section. And what you really need is higher energy data, and in particular data that's in these off-resonance regions to put an upper limit on what these background contributions are. All right, and also, as I talked about, there are these different interferences that you can have. Here's just some examples. You can see that they create large differences. But as you can maybe also see, we have those pretty well nailed down by the data now, of which interference solution is correct. All right, so there have basically been, in the last 20 years, some updates to all of this. And some really nice measurements that have refined all these earlier ones. There are now something like 4 or 5 of these beta delayed alpha measurements, high precision scattering measurements done at Notre Dame, which I have to tout, 32 different angles, 400 energies. They cover a very wide energy range, have uncertainties that are around 1%. A really nice measurement that have come about with the development of recoil separators. This really amazing measurement was done at ERNA, the European Recoil Separator, when it was still in Germany. And they did an unprecedented measurement, although it's a bit higher energy for some of it. But they measured all these possible other cascade transitions, we'll call them. It turns out the ground state transition, which I've been showing mostly, is the strongest at low energy. But all of these, you can also have gamma decay to all these other ground states as well. And those also can have constraint on this phenomenological model. All right. So as I said, these E2, a lot of this data is really, or a lot of these interference solutions have been solved recently. Here's a paper by Carl Brunet and Dan Sayer, his grad student at Ohio from a couple of years ago, where they did an investigation and narrowed this down to 2 different solutions. And then if you take that Sherman recoil separator data that was done the same year and put in that higher energy data, it collapses to just one solution. That higher energy data is up here. The solid and dashed lines are the 2 different solutions. So there's quite a difference in there. So that's completely basically determined now. There's been a lot of development in determining the properties of these subthreshold states through still alpha transfer, but now doing sub-Coulomb measurements. Here's a very recent one by Grisha Rogachev. I think he's still at Florida State, where he measured these to about 10% of AMCs, or the reduced alpha widths. Those reduced width amplitudes, basically, that we saw earlier, to about 10% precision, which is a vast improvement. So now we can try to put all of it together, really like Fred Barker did years ago. So we're doing the same thing, but now we're just taking that also to higher energy. We have tons more data than they had in the 70s. And you put it together with our tool that is the holy hand grenade here for this reaction. Azure is an R matrix code that was developed at Notre Dame by Dick Azuma and Ethan Ubersater. And it allows us to do these calculations with a state-of-the-art R matrix code, sort of all the most worked out theory. And I worked out sort of this R matrix set to much higher energies. But there's always the end problem is, okay, you get a great fit, but in the end, the toughest part of all of this is how do you determine the uncertainty? And that's nasty. You have a lot of measurements, and those different measurements sort of span the range in quality and what they give for the details of their uncertainties. In addition, you have what we usually call cross-sections, but are in reality always just yields. They always have some target energy loss effects that remain in them. You have geometrical effects that you have to correct for. It even turns out that when you get to really high precision, even at these energies, because the gamma ray energies are getting fairly high, you have to do some relativistic corrections, the angular distributions. But you put it all together, and you do a normal sort of chi-squared analysis, you end up with something like, it turns out about a 15% uncertainty, and a value of about 140 keV barns, which is almost the same as what Fred Barker got in 1970, but with an uncertainty that's much, much smaller. But it turns out that this is a bit of an underestimation, because the chi-squared of all these, the reduced chi-squared of these fits is certainly not 1. There are a lot of outliers in the data, a lot of data sets that are inconsistent with one another. And when you sort of do an inflation of the error bars to try to compensate for that, that inflates the error, the total error, up to about 20% of the total. And okay, so here's finally the reaction rate. And you can see that we end up with a pretty significant improvement over some recent, the sort of Notre compilation, which is the standard for most people, I think, and the Kuntz rate from 2002, which is sort of the next best one. So these measurements in recent years, extending the R matrix analysis, have really pushed things down. And that's our results in pretty good agreement also with the Notre 2 potential model analysis, which does kind of a similar thing. And they get about the same central value and about the same uncertainty level. So to finish up, I think that the cross-section of S factor at low energy reaction rate at lower temperatures is about 20%. That still doesn't meet our goal of 10%, but we're certainly made a lot of progress in the last 20 years. And what did this is really higher precision data, and also doing an R matrix fit to higher energy that reduced the ambiguities of the contributions from high energy resonances. These indirect and recoil separator measurements have been critical. And now the problem is that we have all this data, which is, well, yeah, it's inconsistent, yeah, on some level. And so you can't push any lower because, of course, you don't know the right answer. So unless you take, the experiment that you did and say that's the right answer, which some people have done, and that's kind of that's basically what was done in that. Way back at the beginning when I talked about that analysis that said we knew the cross-section to 13%, those guys basically just took their data, said it was correct, and did the same kind of analysis, and so you get a small uncertainty that way. And so that just shows the tension between the different data sets. So what can we do? We have to resolve these inconsistencies, which probably just means making new measurements that are better, because there's not enough information left to really solve the mystery of this by reanalyzing the old data. We could try to push the lower energies, and there are certainly opportunities to do that at new underground facilities, but a lot of the background here is beam induced. So going underground doesn't help you that much. And the cross-section drops so fast, it's pretty tough. But we can also try to measure some of these cascade transitions. We can do these, also learn how to do these alpha transfer measurements better. That's really caused a great decrease in the uncertainty once people figured out how to do these subcoolomb measurements, which eliminate a lot of the model uncertainties in interpreting that data. There's some other details. There's a lot of small things that one could improve to keep sort of hammering away at this. And that's really what it is lately. It's just sort of like banging away at these smaller and smaller things, and it gets harder and harder. Okay, so I'd like to just finish by thanking my comrades here for a nice review paper that we put together on this reaction that has been accepted now and reduced modern physics. A lot of people here from Notre Dame, but a lot of external people. Andreas Best used to be Notre Dame. Now he's in Italy. Carl Brunet, who really helped a lot with the theoretical interpretation of the data at Ohio. Carl Fields, Sam Jones, Marco Pignatari, Frank Timmys for really helping us, particularly me, understand some of the astrophysics interpretations of the data better, or the uncertainties there, as well as Carl Smith, who helped me a lot with the coding of some of this complicated uncertainty analysis, and Ethan Uberstater, who really made the Azure 2 code and did a lot of this. So, all right, thank you.
Thanks, James. So, Notre Dame people, would you like to start with questions? And the others could maybe just indicate in the chat again if they have questions.
How do I like show people again?
What? Is there a question? Ah, there's Lawrence. Then I guess you start. Oh, he just says it's a nice talk.
Oh, Bright was a question.
Yeah, so in the carbon rule of BREIT, we talked about how it's competing mainly between E1 and E2.
Yeah.
Why is there not an M1 contribution in there? Why do we not expect it to E1?
So it turns out, you've got two spin 0 particles that are fusing together, and it turns out you just can't have an M1. The excitations of that system, so yeah. Spin 0 parity plus, I think also. So that's a good. And in fact, there are only electromagnetic or electro transitions possible. You could certainly also have E3, right, higher order effects, but no one has observed that yet in any angular distributions. But it's certainly there.
That's talk too much here. In more general, there's a bit of culture here. The transitions right here, first or first. Second and third is easier. Thresholds, 2 to 2, right?
Mm-hmm.
I was on 2 of many different parts. But understanding in the beginning, 3. The first transition here, 3 goes together.
Mm-hmm.
It's easy, right?
Right. Yeah, it's not. So the
main clue is unusual. I mean, nuclear people belongs to roots here. But intelligent physics, difficult, very difficult.
Yeah, sure. I mean, the triple alpha process is. That's why it remained a mystery.
So local one. Local, yeah. Still close together, right?
Yeah, I mean, what they end up doing is they sort of briefly, they live long enough that you can actually sort of have a sequential, it turns out to be kind of sequential fusion. But it took a long time because no one thought that you could have 3. Yeah. And you get this very sharp resonance, right? That means it lives for some amount of time. Yeah.
And the reason resonance is
here. Yeah. Yeah.
Kind of like in soccer.
Yeah. It gives it just enhances it enough so you can have this sort of triple.
Right.
Yeah.
So I think Manuel had a question from home.
And well.
Yeah. Did you see the question on the chat? What about E0 or EO?
Oh, I did not. I have not used Zoom before, so I did not. All right, we're getting there though.
More.
Oh, here we go.
Was that your answer already? It's hard to understand you here, actually.
Somebody asked about an E0 transition. That's a good question. So for heavy nuclei, you can often get strong, like a strong E0, so electron-positron production or something. But it turns out for light nuclei, for light nuclear systems, often this is pretty small in probability. And for this reaction, it's been measured to some extent that it's just negligible, but it might not be. Once you start getting to smaller uncertainties, even these smaller branches could have an effect, and nobody's studied that really carefully. So it's a good thing for someone to look at.
I want to add a comment.
Hmm?
I want to add a comment.
Sure.
I don't think the E0 will contribute to the on-shell photon. It will only contribute to the off-shell photon, like electron-positron pair production. Because it's a Coulomb, and photon is the transverse photon, so you want couple to E0.
Right, there's no gamma, but you can have, like you said,
Yeah. So you can only see E0 in the off-shell photon, like electron-positron pair production. So you will not contribute to on-shell photon.
Okay.
So its contribution will be 0.
Well, you don't get a photon, but
it will only contribute to the electron-positron pair or other off-shell processes.
Yeah.
It's Coulomb excitation.
It doesn't care if it decays through gamma decay or not, as long as it forms, right? O16.
The photon is on shell, so it will not contribute to Coulomb. I actually have another question. Is that what constrains the resonance tail contribution? Because I sense that tail could be very relevant for the interference between resonances. And what is the physics constraining those contributions? Because it's far away from the pole. So what is the benchmark for the tail?
The only thing that constrains the tail is data. Right? The only thing you can do is measure reaction data in very off-resonance regions where these tail contributions might have a large...
Well, the thing is that you have interference between the resonances. So the cross-section doesn't tell you the individual tail, right? Because they interfere.
Right.
Yeah, that's why I worry. What is the how well is that behavior benchmarked?
Yeah, not well. That's the main uncertainty contribution.
Okay, so it's not clear. At least it's not clear to me. If you have simple BREIT-WIGNER, you will be right. We are far off resonance.
You're definitely not right. Yeah. You have a simple BREIT-WIGNER that, in fact, does not give the cross section in the
okay. Yeah. So you can have in your R matrix you can have a very complicated formula, but I don't know how well that formula is benchmarked.
Well, as far as I know, it's benchmarked quite well. So that is supposed to actually give the off-resonance cross sections a high precision. So that's why people have used R matrix moved to R matrix instead of BREIT-WIGNER. But it's a good question also to investigate. Still, this is an old, it's an old theory. There may be approximations. There are approximations that are made in it, and it's good to investigate if those still hold up when we move to very small uncertainties. So if you're a theorist, please investigate that.
Yeah, we'll think about it.
Okay, are there any more questions? I would say if that's not the case, then let's thank James again. Thanks, James.
Thank you.